Welcome back. This next one's called moving zeros to the end. Write an algorithm that takes an array and moves all of the zeros to the end, preserving the order of the other elements. So they have an example here. They call the function move zeros that we're going to implement. They pass it a sample array. Notice how zeros are scattered throughout. And the result should be all of the zeros were placed at the end while preserving the order of the non-zero elements. Notice this is how they occurred. 1, 2, 1, 1, 3. 1, 2, 1, 1, 3, 1. I missed that last one. But yeah, so you're essentially grabbing all the zeros, put it right at the end. So go ahead and try this one out. See if you can get it. And resume the video when you're ready. I'm going to show a couple ways of going about this. One is with using link. So I'll start there. This is kind of the one-liner that's short. Not the most efficient thing, but it reads nicely and it's on one line. So first things first, I'm going to think of splitting the array into two subarrays, one containing the non-zero numbers and one containing the zeros. And then if I do that, I can simply append the zero collection on the end of the first one, right? So that's sort of the strategy here. I could say array where, let's use our filter, right? And we'll pass a lambda. And for this, we're going to grab the ones that are not zero. You could say n is not equal to 0, right? And so this gives us all of the numbers in here that are not zero. The 1, 2, 1, 1, 3, 1. Then imagine I had another version of this, right, where I said where n is equal to 0, right? So this one would make a collection where all are zeros. This is a collection where all are non-zero. And then what if I do something to sort of glue them together? We know that enumerable has this concat method, short for concatenation. That's like what we do with strings when we add them together. You know, you remember something like hello plus world, right? That's concatenation, the plus operator. We're not doing arithmetic math here. We're just taking these two strings and sort of gluing them together, right? That's concatenation, and we can do the same concept with collections, where we just put all the values at the end of the first collection. So that's what we'll do here. And then one last problem, we know that each of these filter wheres will give these IEnumerable collections, but we have to give an integer array back, right? So we know that these enumerable collections have a method called toArray, right? And each of the collections we made were of the type integer, so we should be fine there. We should be getting an integer array back. I'll go ahead and run this. And it looks good. Yeah, so non-zeros, then tack on all the zeros. So that's cool, but you might think, you know, what would be wrong with this? Why wouldn't I just want to necessarily use this? Well, my problem, and why I'm going to do another way, is that we kind of go over the collection twice, don't we? I mean, think about what where would do. Imagine someone asks you, they give you an integer array collection, and they say, hey, give me all the numbers that are not equal to 0, just like we said here, right? When they do that, you're bound to look through the entire array, right? Because you never know that last element. If there's thousands of elements, you have to go through every one, because that last one could be not equal to 0 as well. There's no real shortcut, unless, you know, if you talk about into sorting collections first, then you could make some optimizations. You could exit early, but just assume in this situation, right, where we're not sorting, the numbers could be in any order. you have to look through the entire collection. There's no way around that. We're analyzing every element. And so I'm doing that twice here, right? I'm going through the entire collection twice. I went through every element once to check if it were not equal to 0. Then I went through the whole thing again to check if it were 0. And so that's kind of wasteful and doesn't really sit well with me. So if this wasn't important and just a one-time method call or not called often, probably not a big deal. Or if your array size, you knew it wasn't going to be very large, probably not a big deal. But it'd be good practice to do our own, and I think it's better in this case, so I'm going to do that way too. So for this, let's start by making the integer array that we have to return. I'll call it result. I often name things that I return that way. And we got to make a new int array, right? And we know how to size it. The size isn't going to change, right? We're just putting the zeros at the end, but it still has the same number of elements. So we could size it like this. Okay, so we have our own integer array. Nothing's in it yet, but we have it sized appropriately. So now I'm going to, the main idea is going to be like this. Int num in array. For each integer in the array means we're going to iterate over all of the elements and look at them in turn. And we're going to say, basically if num is not equal to 0, do one thing, else, handle the case where it is equal to 0. And so I'm using this for each loop because I was going to make up my own indexing. I'm going to use two indices here. I'm going to have one from the front and one that points to the back of this array. So I'll call one, let's call it front index, and that will be 0. We know we start with 0 in arrays. There's 0-based numbering. And then I'll call one rear index, which will be what? Array length minus 1, because we have 0-based numbering. If you didn't have that minus 1, you would extend beyond the bounds of this array, and that would be an error. So now that we have that, if the number is not equal to 0, it should go at the front of the array, right? So let's use that. Let's say result front index equals num, right? And then I'm going to add one special little thing here at the end, because we don't want to always leave front index the same, right? If we did, it would always overwrite in that first element of the array. So we need to increment it when we're done. This is a postfix notation, which means that when we access the array with front index, it's going to use the current value first, and then after this whole assignment is done, it's going to increment front index. It's sort of like if I did it like this and then said front index plus plus. Just go ahead and increment it. But when I do it this way, it's nice. I can do it all in one line. Be aware that you can also do it this way, but the problem with this is that it will increment the front index first. So it'd actually bump this up to 1 and then insert in slot 1, and we would actually miss the front of the array, so that would be bad. If you were, if you really wanted to do it that way, I suppose you could just initialize at -1, but I'll go ahead and do it like this. And so you could imagine the situation is very similar for a value that's equal to 0. In fact, I'll even copy this line. And instead of the front index, what do we want to do? We want to put the zeros at the back, right? It doesn't really matter what order the zeros are in, so I'm just starting at the end of the array and kind of loading them, moving toward the front. They're all zeros, so it doesn't matter. And then, of course, we have to decrement our rear index. Otherwise, we'd always put the elements at the very end of the array and keep overwriting. So that would be bad. And yeah, same idea. We put it at the end, so it will use the current value first, and then it will decrement it after this whole line, this whole operation here is done. So that's handy. And then at this point, you can imagine each of these, this front index and this rear index, sort of working towards each other and meeting in the middle. And they meet in the middle when all of the elements have been processed. This for each will go through the numbers in the array in order. So our order should be preserved here. And then I can say simply return result. Now, yeah, I typed more here. But what I like about this is that I went over the number collection only one time. Remember how I did it twice in the first example? So there's something good to be said about that here. I like that I'm processing it once, and for each element I'm making that decision. I'm saying, you know, are you a 0 or are you not? And I can examine that for each element while I'm there, instead of doing one pass for the non-zeros and one pass, another whole pass for the zeros. So I'm going to keep this solution. I'll go ahead and submit that. Looks like we're clear for takeoff there. Cool. Here's a good take on it. Order by x such that x equals 0. Okay. Nice and short. This was like example 1 that we did, where I just didn't care for it because it goes over the whole collection twice. But yeah, that's works. Yeah, looks like other people roll on their own too. I think the common myth here is that people tend to think that if code is only, if it's shorter, if it only happens on one line, that there's less work happening. And the problem is you can't make that conclusion. You'd have to actually look how these wheres are implemented. But that's probably misleading to people, and they think, oh yeah, I did it all on one line, so it's got to be short and efficient. Well, probably a lot of the time, but not necessarily. So something to think about. Go ahead and send whatever you came up with or questions, and then otherwise we will keep moving. Thanks for watching.